Good afternoon, everybody. I hope there will be no technical problems or any other problems today. And let's continue our lecture. I first want to clean up some definitions that I missed at the beginning of the course. It just occurred to me that it doesn't make sense to include them later on because they fit perfectly to the very beginning. So before we go back to counting paths and start the new exciting topic of adjacency matrices, let's still do some boring definitions, but we have to be on the same page. In a way, they are completely obvious, but for legal purposes, I have to state them precisely. So first we have a definition. I hope you can you read what I write? Nobody objects?
Yes, it's okay. It's okay.
Perfect. Because this is we're also wondering why it didn't work in October, and our conjecture is that it was because of a different angle of the light coming from the sun. Because now this camera giving me two blackboards gives me better vision than the other camera. Anyway, so I want to define a subgraph. Oops. So we say that the graph F which remember is a quadruple, F0, F1, SF, TF, is a subgraph of a graph E, which likewise is a quadruple. I need to introduce this notation so that we are on the same page. And you see, now that I have more than one graph in play, I decorate the source and target maps with the letters, with the letter denoting a graph, because we have to distinguish these source and target maps from these source and target maps. It's only when we have just one graph, it's a redundant, sorry, this is E1, decoration. Okay, which we write as, in the simplest possible way. So F is contained in E. If the following conditions are satisfied. So first, of course, as you could expect, F0 must be the subset of E0, and F1 must be a subset of E1. So all edges of F are edges from E, and all vertices of F are vertices of E. And now this is important. When I look at the source map of E, but I restrict the domain to F0, and then I take the target map of E, but F1, but I restrict the domain to F1, and I take the union of these two images. Of course, I have to demand that this be contained in F0. Okay, so this is a condition. It's sort of in addition to just F0 being the subset of E0 and F1 being the subset of E1. We also have to have this condition on the images. Otherwise, the restriction to F1 of the source and target maps will not work. I mean, we have to have that beginnings and endings of each and every arrow has to be in a vertex, which is in a subgraph. And now the third one, no surprise. By definition, SF and TF, which of course are defined as maps from F1 to F0, are restrictions of SE and TE, which go from E1 to E0 respectively. Okay, so this is a pretty obvious definition. An example, which is in fact quite geometric in nature, is that I have a graph which has just one vertex and one arrow. So we must have a loop. And of course, you can view it as a subgraph in a graph which has 3 vertices and 3 arrows. Okay. And by the way, this has a geometrical meaning. When you go to graph sister algebras of these graphs, this will be the equatorial Podlesh quantum sphere. There will be just a circle. So geometrically speaking, what we are talking about here, we have a 2-sphere. And we insert a circle as the equator of a 2-sphere. So in classical world of algebraic topology, or topology simply, this is what you will have. The equator circle included in a sphere. Okay, but this is a very nice example of a subgraph, very simple. Now, I also want to define the intersection graph and the union graph. I sort of mumbled about it using slides, but let's do it systematically. And here comes another definition. Oops. I need a bigger piece of chalk. So let F and G be graphs. Assume that SF and TF agree respectively, okay? Agree respectively with SG and TG on the intersection of F1 with G1. So I take the edges of the graph F, I take the edges of the graph G, I take the intersection of these two sets. So I'm looking at edges which are both in F and in G. And when I apply the source or target map from F, it has to agree with the source and target map from G, which of course implies that you also have to have an appropriate intersection among vertices. If this condition is satisfied, then we can define the intersection graph Okay, so this is what we are defining in the following way. So F intersect G. Of course, it must be a quadruple. When it comes to vertices, it's just F naught intersected with G naught. When it comes to edges, it's of course F1 intersected with G1. And you see, by saying that SG and TG agree respectively with SF and TF, of course, I mean that there is an appropriate intersection of vertices. Otherwise, we wouldn't be able to talk about an agreement. So this word agree is strong. Okay, so that's Now I have to also write down these source and target maps. So it's S cap and T cap. And now I have to define these source and target maps, but the definition is obvious. But let me write it down. These are, of course, maps from F1 intersect G1 to F0 intersect G0. And they are given by the formula that for every E in F1 intersect G1, we have that S cap of E is equal to SF of E equal to SG of E. And of course, likewise, T cap of E is equal to SF, TF of E is equal to TG of E. It makes sense because I assumed that they agree. Okay. And now also let me give you a geometric example of such an intersection. Okay, let me erase the subgraph. Okay, so let me take actually two identical graphs. They have two vertices and two edges. But as I suggest, well, maybe I should, to be more precise, I should have some notation. So V, W, then this is W, V prime, and let it be F, F prime, but this is the same E, all right? So now with this notation, you see that the intersection graph will be just the circle graph, E and W. And again, it has a geometric interpretation because what I'm doing here, I'm taking two disks, two different disks, but I declare that they have common boundary. Think about it as two hemispheres, right? The two hemispheres intersect over the equator. Okay, one more boring definition of the union graph. So the preamble is very much like in here. Let Fg be graphs, assume that S and F agree respectively with Sg and Tg on F1 intersect G1. You know what? I'll just erase this one. So then we can define the union graph. I know I'm cheating a little bit, but this is too boring to write it twice. Then we can define the union graph. Now, this is not cap, but cup. It's funny because we'll have a teacup. Okay, which again is a quadruple, but now the set of all vertices is the union of sets of vertices. The set of edges is the union of the sets of edges. And now we have S cup and T cup. Yeah, it makes me thirsty when I say teacup. All right, and now how do we define them? Well, here definition's only slightly more involved. Now we'll have to do cases. So this maybe I will do like this. I'll erase it. And the condition is as follows. I mean, formula is as follows. I take S cup of E, and this is equal to SF of E if E is in F1 and is equal to SG of E for E in G1. And you see it makes sense because if E is in both F1 and G1, these guys agree. And likewise for T cup. I just replace S with T. Okay. Right. And again, a very simple example.
Excuse me.
Yes, yes, go ahead.
Does this what you wrote there on the right is too small and I can't
Okay. I will, you know what? I will just write it on the other blackboard. Yeah, that's perfect that you say such things. Okay, so I have S cup of E. So the quantifier is on this blackboard for all E in F1 union G1, okay? But now I have to do cases because I cannot write a uniform formula. So this is equal to S F of E for E belonging to F1. And this is equal to SG of E for E in G1. And as I said, so this is a definition. The formula makes sense because if E happens to be in both, then these two agree, right? And likewise, it's an identical formula for T cup. All I do, I just replace S with T. So it's TF of E if E is in F1, and it's TG of E if E is in G1. Okay, so now this is clear. Right. This ends the definition, and I can now give you, I hope it's visible right now. Let me give you another example. So maybe this will be examples. And well, basically, I want to do the same thing. Well, let me cheat again. So I will now take the union of these two graphs. So what you see is the common part, the intersection is just the circle. So when I unite these two graphs and the intersection is a circle, well, what I'll get will be this. I'll have F going to V, and I have F prime going to V prime. And now, this also has a topological meaning because I'm gluing two disks over their boundary, and what I get, lo and behold, is a two-sphere. So when you go to graph sister algebras for these graphs, this will be the celebrated Teptit algebra, which has an interpretation of the sister algebra of continuous functions on a quantum disk. And of course, when you glue two disks over the boundary, what should you expect is to get a sphere. And this is again the equatorial Podlesh quantum sphere, which everybody knowing quantum groups has heard of. All right, so we have definitions, we have examples. I just want to make one elementary remark, and then we sort of continue with more interesting things. But I want you to remember it. The union graph exists if and only if the intersection graph exists. Right, because all that we have as a requirement is that the source and target maps agree respectively on the intersection. So this agreement is on the intersection regardless of whether you are defining the intersection graph or the union graph. Whether you want to do cases for these formulas for S cup and teacup. I have to be careful to not to confuse two words. One is cap and one is cup. And this is how it should be, because later on we will see that if the inclusion of the intersection graph in both of the graphs is admissible, then also the inclusion of graphs in the union graph is admissible, which is a very nice thing, which I proved to you from when using slides, at least part of it. Okay, I think we are done with the things which I skipped before. Yes, because now we go to paths.
I have a question.
Yes, go ahead, always.
Because I understand it and it's intuitive, those definitions.
Yeah.
But are there like precise? I mean, because this sets of F1 and F0 are just arbitrary sets.
Yes.
So we can have graphs which looks the same.
Yes.
But they won't have intersections.
Correct, but this is exactly as in topology. I can tell you, well, I take two circles. I take two different circles. And then I can say, well, these circles are not so different. They have one common point. This is it's exactly the same here. This is why I made this observation here. I labeled the edges and vertices, because if I just draw a picture, then you have no idea. I might as well mark it as E prime and W prime, and then it will be like disjoint union, right?
And wouldn't it be better? Wouldn't it be better?
Yeah.
For us to have a definition in which we can take, for example, an intersection of identically looking graphs, which are labeled differently. For example, we just take an, I don't know, bijection of one of, in those definitions, we take intersection. Why?
No, because I repeat, it's exactly like in classical topology. Just because you have some things that are homeomorphic, like you have the unit sphere, right? So then you would forbid yourself from drawing two different unit spheres. The same is here. It cannot be that we just have a shape of a graph. Of course, these two graphs are isomorphic, but two disks are homeomorphic. So that's the same story. I still can take as many copies as I want.
Piotr,
That's true.
Piotr.
Yeah.
Actually, you can make this more precise. So what you can do is, I mean, like we have defined like at least an inclusion of graphs, right? I mean, like that we have defined more or less like formally. So what you can do is you can take your two graphs that possibly are not identified edges. You take, and then you can define their intersection with respect to an ambient space, with respect to an ambient graph. So like you have like F and G sitting inside H, and the way they sit inside H determines also like what is their intersection. And the intersection will be, you can like either say, okay, like inside H, or you can say also like, you can also define it categorically as the, I think the pullback inside the category of graphs.
Yeah, but I don't agree that this is more precise. And what I wrote is absolutely perfectly precise. It's what we are talking about is intersection of sets, okay? And if I intersect two 5-element sets, well, then it all depends on the labeling. Yeah.
I'm not saying it's less precise or more precise. I'm saying it's you can define it formally.
Yeah, sure. I understand. It's like you have the universe where you embed everything, and then it has its place, and then you know how to intersect it. But
yes, I mean, for example,
I read you, but I don't see any purpose in doing so.
Yeah, so there's a purpose. For example, if you have one loop,
yes,
as F, and
yes,
and the graph G with two loops,
yes,
like say for example U and V, like O2.
Okay, so this is my F, and this is my G.
Yes.
Okay.
And then like, so now you have it O2, and you could even like say take G to be like an extra additional disconnected loop. So instead of G being only O2, like G being O2, direct sum with the circle.
Yeah.
And then it heavily depends upon like how you what you identify with what. And so you could say just like, okay, F and G like embedded inside H, like how is F embedded inside H and how is G embedded inside H?
Yeah, but I still claim that effectively it boils down to labeling.
But it's not just a matter of like how do you say, like, yeah, labeling.
Yeah. I mean, the same thing. If you want to say how these two graphs F and G relate, I mean, you cannot, because these two vertices can be different. And then the intersection is just empty. The union is just disjoint union, right? Or you can declare that these two vertices are the same. Well, then you can have either O3, if this loop is none of these loops, or if this loop is one of these loops, you'll still have O2. So when you take the union, right? So without the labeling, I cannot make sense neither of the union nor of the intersection.
Yeah.
I must use labeling. That's why I was careful here.
I'm convinced.
Effectively the same of what we are saying, I believe. Right? Alex?
Yes.
Yeah, okay. So let me finally go and do something more interesting, hopefully. I have to skip. So I put it at the beginning of the lecture notes, yeah, because this is where it fits. And I apologize for messing it up because I should have done it more systematically, but somehow it didn't occur to me. Okay, so now I flip the pages, many pages, including our 3-hour-long proof. Yep. And before I go to the adjacency matrices, I want to state a conjecture. Is Oscar logged in? No, I don't see Oscar. That's strange. Oh, he's not on the Zoom and he's not in the room, which doesn't look good because he has to do a proof.
Is it regarding the Patterson result? I mean, like I could give it.
Okay.
I could give it. Nice.
Okay, great. If he doesn't turn up, I mean, we'll still have a break, so I'll call him.
Mm-hmm.
Okay, so this is our joint conjecture. Which is, if you want, a different form of this long K theorem, which we proved some time ago. So what are our assumptions? So let E be a finite graph. No, more. Let E be a graph with n edges. Let E be a graph with a finite number, but at least 2 edges. And this time, okay, and we have the same definition of K, okay? And let K be a number between 1 and n. And here, instead of assuming that we have absolutely no loops, and this was Oscar's idea, assume that all loops, if they exist, all loops are at least of length k. I need another piece of chalk. Okay, so this is where we change our assumption. Instead of assuming that there are no loops in this graph, we assume that all loops are at least of length k. And now we conjecture then there are at most k times p and k different paths of length k. And of course, the bound is optimal. All right. So you see, when we assumed that there are no loops, we didn't have this k. And the graph which was optimal, I mean, the graph for which we had this bound achieved was the following. We had k plus 1 many vertices. So v0, v1 up to vk. And here we had some, say, v1 edges from v1 to v0 to v1, v2 edges from v1 to v2, dot, dot, dot. And finally, we had vk edges from vk minus 1 to vk. And then we had these bi's differing from each other by at most 1. Okay. And then when you compute the number, this would be this number defined earlier, p and k. So now our conjecture boils down to the following observation, that now we presume, but we have to prove it, that you can arrange this graph into a loop. So you go from actually vk to v1 to v2, dot, 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 you go around. And here I have vk minus 1. And here you have, of course, b1 edges. Sorry, here you have b1 edges, here you have b2 edges, and here you have bk edges. But now you can see that when you look at all possible paths of length k, you can start them at any vertex. You can start them at vk, v1, v2, and so on. So you have k possible starting places. When you look at this graph, the only place where you can start a path of length k is v0. There's no other place where you can start a path of length k. And here you have k places to start. And of course, when you take any of these vertices as the starting point, you'll have exactly as many different paths, regardless of which vertex you take, because it will always be just the product of all bi's from I equal 1 to k, right? Which is this number p and k. And this is why I multiplied by k, because now I have k starting point. So the bound is achieved is easy, but now we have to look at this 3-hour-long proof and see whether we can tweak it into a proof of this conjecture. I find it very interesting. It makes combinatorics more difficult, I believe, but I think it's still manageable. What I find very tough is if you would change in our assumption of a conjecture, if we would change it to the assumption that we have loops of length at least L, where L is greater or equal than K. Then I feel lost. I don't even know what to conjecture. Right, of course, if we assume that we have smaller loops, then we are in complete mess because we can repeat edges and, well, you can forget it. It's very, very messy. But we should be able to do it in this case, because as long as L is greater or equal than K, you still have this first property that in any path of length K, you cannot repeat edges. I said vertices. You cannot repeat all vertices as well. You cannot repeat edges. Well, not quite. I mean, you can have you can have at your path of length K is a loop, so you have the end point and the start point the same. But you see what I mean? With this assumption, one of the first things that we proved towards this big K theorem, I mean K path theorem, was that when we take any path of length K, we do not. Well, actually, it was true when we have no loops for any path of any length, that we have don't repeat ever any edges. But now here, since we allow loops that are sufficiently long, well, of course, we can repeat edges if our paths are very, very long. But when you restrict ourselves to paths of length which is smaller than the length of the shortest loop, then we cannot repeat the edges. So then the combinatorics should be much in this spirit. But when I take L, which is bigger than K, I, to be honest, don't even know what to conjecture. So if you have any ideas, just let me know. For the time being, what we conjecture with Oscar is that if the shortest loop is of length at least K, then this should be the biggest number. And this is the graph realizing this bound. Okay, I think we can open a new chapter of the lecture. So we are done with paths. Let's do the adjacency matrices. And this is very simple, but computational part of the lecture. So I'm now giving you tools for computing things. And in fact, this is, again, very intuitive, and very straightforward. But I really would recommend that you pay attention to these adjacency matrices, because when you go to K theory of graph sister algebras, then these are precisely the adjacency matrices which compute K groups. So somehow right now I'm doing it for paths. This is baby stuff. But later on, when you want to do something more serious, like computing K theory of graph sister algebras, then what you do, your first move is you write the adjacency matrix of your graph. And then you have explicit formulas due to Rayburn and Szymański that tell you how to compute K groups. This is very, very remarkable, because computing K groups is often quite a difficult task. And for graph sister algebras, you have an algorithm. A computer can compute K groups. I give you a graph, I program a computer, and the computer gives me K groups. All right, and it does it via adjacency matrices. Okay, so what are they? Well, for starters, they work only for finite graphs. I mean, if your graph is infinite, then, well, you just have an infinite matrix. And in this theorem of Rayburn and Szymański, of course, you want to handle infinite graphs. But then instead of speaking about matrices, you look at maps from, say, abelian groups Z to Z, stuff like this, okay? If you have a linear map from Z to Z, it's in a way an infinite matrix. So there is a way to handle it just as with matrices. But in order to really speak to matrices, I need to have a finite graph, and when it comes to counting paths, which is what I'm going to use adjacency matrices for right now, I have finite graphs anyway. Okay, but I don't want you to feel that this technology is limited just to finite graphs. It's just for counting path purposes that we want to have finite graphs. Okay, so as I warned you, let E be a finite graph. The adjacency matrix A of E is the square matrix well, actually, I should say A. Because, you know, better linear algebra issue, it has nothing to do with graphs. When I have a homomorphism between vector spaces, I cannot just say the matrix of this homomorphism because it depends on my choice of a basis. So it's the same thing here. If I relabel my vertices, then I'll get a different matrix, okay? So I have to write A square, actually. So I have to correct it in my notes. A square matrix whose entries are labeled by pairs of vertices and when I say pairs, I mean ordered pairs. And each VW entry is simply the number of all edges from V to W. Okay? So this is a very simple definition. The size of this square matrix is E naught times E naught, right? When you take the number of all vertices, that's the size of your square matrix. But I can, you know, permute my vertices. This would be like permuting rows or columns. So I cannot write that square matrix because when I look at a graph, it's a quadruple and I have sets of vertices, not ordered sequences of vertices. So just by saying that I label my entries of a matrix with vertices, I'm not telling you in which order I take vertices. And this is why it's not uniquely defined. But once you choose your ordering of your finite set, then you can make the following observation, an elementary remark. If you take the opposite graph, then the adjacency matrix of the opposite graph is the same as the transpose of the adjacency matrix, okay? Because what is taking the transpose of a matrix? It's replacing rows with columns. So it's like flipping over V to W and W to V. But when I flip over V to W and W to V, what I do effectively I replace source with target and target with a source. I'm basically talking about all edges going from V to W, but in the opposite graph. Okay. So speaking about all edges from, so if I just take the transpose, right? Then I would be speaking about all edges from W to V. Yeah, because taking a transpose means that I replace, I switch these two vertices. Okay. But talking about all edges from V to W, it's the same as talking about all edges from, talking all edges from W to V is the same as talking all edges from V to W in the opposite graph, where you have exactly source and target maps interchanged. So this is just an obvious formula, good to remember. Of course, it's under the assumption that in both cases, I already fix the ordering of my vertices. Okay, let's do some examples now. Well, first, if I take, well, let me do it like this. I will simply have here graphs. And here it's identity matrix. Doing such a table in LaTeX is not fun, so I wrote it with full English sentences, but on a blackboard it's more convenient like this. So imagine I have one single extension of O2. Alex knows what I'm talking about. So this is like a Kuhn step-less algebra. Okay, this is my graph. So what is the adjacency matrix? First, let's fix the size, and let's do the labeling. So let it be, say, 1 and 2. Of course, I could order it the other way around, and then I would get a different matrix. But it would be like a change of basis in linear algebra. Okay, so this is a 2 by 2 matrix. And here it's 1, 2, 1, 2. And I have two edges from 1 to 1. I have one edge from 1 to 2. I have 0 edges from 2 to 2. And I have 0 edges from 2 to 1. Okay, so this is the adjacency matrix for this graph. Now let me take such a graph. Again, 1 and 2, but now I put 3 edges like this. Well, I have 0 edges from 1 to 1. I have 3 edges from 1 to 2. I have 0 edges from 2 to 1, and I have 0 edges from 2 to 2. Okay, so this is a very simple matrix again. I have 2 more examples, so let me continue here. Again, graph and matrix. Okay, so actually this is a graph which Alex pointed to just some time ago. But now when I draw it like this and I call it one graph, then of course these joints of the circles. I just label vertices 1 and 2. You see, now this is diagonal. I have no edges from 1 to 2 and from 2 to 1. So when I look at off diagonal, this is 0. But I have 2 edges from 1 to 1, and I have 1 edge from 2 to 2. One more example. Now let me take 3 vertices. And this is like a graph optimizing the number of paths of length 2 when you have 5 edges. Okay. So I have 0 edges from 1 to 1. I have 3 edges from 1 to 2. I have 0 edges from 1 to 3. I have 0 edges from 2 to 1. I have 0 edges from 2 to 2. And I have 2 edges from 2 to 3. I have 0 edges from 3 to 1. I have 0 edges from 3 to 2. And I have 0 edges from 3 to 3. Okay? So this is the matrix you get. All right, so these are examples. It's a very intuitive definition, so it's easy to remember. But despite it being so easy, it's a very important definition. And you'll see just in a second what a nice computational tool it becomes. So let me make the following observation, which is actually a proof of a simple but important proposition. So in a finite graph, E with n edges, consider all paths of length k starting at a vertex V and ending at a vertex W. Well, here, actually, I'm not assuming that V and W are different vertices. I'm not assuming that the graph has no loops. All I'm assuming that the graph is fine. You see, I have absolutely no problem with loops. Okay. So now, if I decompose K into the sum of 2 positive integers, so if K is equal to K1 plus K2, with K1, comma K2 in n less 0, then each path P from V to W decomposes into 2 paths. So it decomposes into a path P1 of length K1 with the beginning being V and say end being U. So it's some other vertex. And a path P2 with the beginning being U and the end being W. All right. That's, I hope it's clear. I just have my vertex V, I have my vertex W, and I have a path of length K. Well, it means that this path has K edges. So I can simply take first K1 edges, and it has to end at some vertex U, right? So this will be a path of length K1, and this will be a path of length K2, with K1 plus K2 equal to K. It's always possible to decompose such a path of length K into two paths. So this is P1 and P2, and if you want P1 times P2 is equal to P. Okay, and it's sort of like with a logarithm. The length of P1, P2 is equal to length of P1 plus length of P2. Okay, so this is exactly what I'm doing here. So now, if I denote by NKVW, sorry, hence the number NKVW, which stands for all K paths. And I say K path, I mean a path of length K. Of all K paths from V to W equals the following sum. So I can write VW equal to the sum over all vertices U. And now I take NK1 VU times NK2 UW. And this is true for any U for any K1, K2 under these assumptions. And it's clear because once I fix these vertices, V and W, and I look at all paths of length K which begin at V and end in W, well, I can always ask where do they factorize, at which vertex. And if I want to factorize them into paths of length K1 and K2 respectively, then I just look at all possible vertices where P1 ends and P2 begins. Of course, it can happen that this path of length K does not factorize through some vertex U, okay, which is, well, just a vertex in E, but then one of these numbers will be simply 0. So this means that we have shown the following proposition. Let me now erase it. Right, let's make it clear. If I have a V here and W here, and imagine that there is a U through which, and there is no path of length K from V to W which factorizes through this U. So what does it mean? It's not possible that there is a path of length K1 here and a path of length K2 here, because if such paths existed, then we would have factorization. But if we don't have such factorization, it means that either we don't have any paths here of length k1, or we don't have any paths here of length k2, which means that one of these two numbers here is 0. And when we look at, so effectively we sum over all vertices such that such factorization into paths of length k1 and k2 occurs. Okay, so the formula is correct. But I'm sure you recognize that this is nothing but matrix multiplication over here. So thus we have shown the following proposition. Let E be a finite graph. Of course, we're talking adjacency matrices. And let ALE be the generalized or a generalized, be a generalized adjacency matrix which is defined as follows. Adjacency matrix of E so whose entries are again labeled by pairs of vertices but each VW entry is defined as the number of all L paths from V to W. Okay, so this is just notation. I'm just explaining to you what I mean by a generalized adjacency matrix. And again, we have the same problem. We have to fix the order in our finite set of vertices in order to be able to compare formulas in a meaningful manner. Okay, so what is it that we have shown? Well, then, and this is a very beautiful formula, for any positive integers k1, k2, if I take the generalized or a generalized adjacency matrix ak1 plus k2 of my graph E, this will be nothing but ak1 of E times ak2 of E. So this is what I meant. I mean, for this formula to make sense, I cannot write this matrix for one ordering of vertices, this matrix for another ordering of matrices, and this for yet another ordering of vertices. For such a formula to be meaningful, like in linear algebra, when you want to write equations which are given in a basis-free manner by, say, homeomorphisms, composition of homomorphisms, and you want to express them as multiplication of matrices, you not only have to choose a basis, which is, say, finite, but you also have to order it. Okay. And this is a very beautiful formula. Because you see, you can guess now what I'm driving at. And I have a tool for counting paths of length k. Because all I need to do is to raise my adjacency matrix to kth power and add up all entries. And this is what the computer can do for you. Okay, so you have first, well, what I just said, I can write it as a corollary. For any positive integer n, we have it a and k, sorry, a and e is nothing but a e to the power n. And proof is immediate. So the statement holds. Obviously, for n equal 1, right? Because then I have a tautology A equals AE. And the induction step is given by the foregoing proposition. With k1 equal to n and k2 equal to 1. Okay, so I assume by induction that a and e is equal ae to the power n. So I want to prove it for an plus 1, but I just use this proposition and I write it down as a and e times ae. But by the induction assumption, this is equal to ae to the power n, so it's ae to n plus 1. It couldn't be any simpler. All right.
So it's actually also true for n equals 0, because then we have identity matrix and we have exactly one path for each vertex of length 0.
I guess you're right. I guess you're right. Yeah, I guess you're right. This is a beautiful remark. Yes, absolutely, yes. Uh-huh. Yeah, I'll add it to the notes. Thank you very much. Yes. Of course. A0 of E is always, for any finite graph, just the identity matrix, where the size is the number of all vertices. Yeah. Because when I have paths of length 0 are vertices. So there is no path of length 0 between any two different vertices. So we are left with just the diagonal. And, wait a second. No, yeah, of length 0, of course. So even if you have loops, you don't care because loops are of length bigger than 0. So the only path of length 0 from a vertex to itself is this vertex. So you have just once on the diagonal. Perfect remark. Yes, you're absolutely right. Mm-hmm. Yeah, I can even revise it and start from 0. Mm-hmm. But then, you know, this is a convention. What is the power 0 of a matrix? So I prefer to keep it as a remark. But of course, well, actually, at least here, well, maybe for the powers, it's better to be positive. But in this proposition, I think you're absolutely right. I can just completely skip removing 0. And this is still true. And the factorization of a path, when simply I write k is equal as k plus 0 or as 0 plus k. This is a perfectly good decomposition. Yeah. And then I write that ak plus 0 is equal to ak times a0, but a0 is 1, so it's ak. Yeah, thank you very much. So here I'll upgrade it in the notes. Absolutely right. Here 0 is allowed. Here since I'm writing power, well, I mean, that's just consistent convention, but I can have it as a remark. Good. And now I have a corollary, which is the corollary I wanted to end with. Oh, Oscar, welcome. Good. He turned up. Great.
Hello.
Hello. I was worried about you because you didn't turn up at the beginning. You missed your conjecture.
Excuse me, could you repeat, because my connection is a little bit unstable and I didn't hear you.
We were worried about you because you weren't at the lecture from the beginning, and in particular, you missed your conjecture.
Oh, sorry. My colloquium took a little bit longer than I expected.
Anyway, no problem. Okay, and this is really, really crucial corollary, which we will use over and over again in exercises, okay? For any finite graph E, the number of all k paths in E is given by the following formula. I take an adjacency matrix AE, I raise it to the power k, I take its entries labeled by vertices, and I sum it up. And the corollary is immediate, right? Because it comes from the previous, it's a corollary of a corollary. Because this, by definition, adding all entries of this matrix will give me all paths of length k. Because what I'm doing, I'm taking all pairs of vertices, and for every pair of vertices, I'm counting all paths of length k. So when I take all pairs of vertices, I have counted all paths of length k. So adding up all entries in this matrix will give me all paths of length n. But because we have this equality, I have this corollary. And this is very practical. And now, since I still have 16 minutes, so today I was faster than assumed, I will show you how to do this on these graphs that we used as an example of the K theorem, the K-path theorem. And because I have 11 of these graphs, I want somebody to finish it at the recitation class, but because I still have a 15-minute left over, let me start myself, okay? Are there any questions? So all this is very easy, but it's important. Okay, so I will now draw the first graph. And I will be counting. So what I want to do, I want to count the paths. So when I was lecturing about it, I just asked you to believe that the number of all k paths is such and such. And you can see the pattern here. Somehow most difficult counting is when we have a graph which is very connected but still not in the final form, because then it's very difficult to really compute by hand all paths of length k. It's messy. On the other hand, when your graph is very disconnected, you have many vertices, then it's actually awkward to compute this one because you have huge matrices. And have a huge matrix, raising it to even a third power is a little bit of a mess. And it might be faster just to compute it by hand. But then when you have fewer vertices, then actually combinatorics, you have more connections. Your graph is more connected. You have more paths. And then really looking at all possible paths is a bit of a mess. And it's faster to raise this matrix to third power and add up the entries. So let me do as much as I can. With the 11 graphs. So first I have to draw it, which is already quite a task. But now you'll have really, really non-trivial example. Oh la la. Okay, I hope I got it right. So this is this beast. And I have to label my vertices. Okay, how about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So taking the cube of 12 by 12 matrix is a bit of a daunting task, but it will have many zeros. I'm not sure I like doing it, but okay, let me start. There are no loops, so there will be, on the diagonal, I surely have zeros. So I hope it will fit here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, it fits. This is our matrix when it comes to the diagonal. Okay, from 1 to 2, we have 2 edges. From 1 to 3, no edge. From 1 to 4, yes, we have 1 edge. From 1 to 5, yes, we have 1 edge.
Piotr?
Yes?
You could like also compute 2 matrices. I'm like they're disconnected, right?
Sure. This will be a block diagonal thing. Yeah. That's clear. Yeah, surely.
Like to keep it more.
Surely, but I want you to see it. Of course, it will be divided. I'll have 7 and 5. So 1, 2, 3, 4, 5. So here's the cutoff. Yeah, thanks. 0 and 0. Okay. That's another thing. Maybe I should have written that if I have this is another thing to be added. I take the disjoint union of graphs. My graph is a disjoint union of graphs. So if you want, we defined already the union graph. So the disjoint union graph is where by assumption the set of edges is the disjoint union of the sets of edges, and the set of vertices is the disjoint union of the sets of vertices. And then, of course, the condition for the existence is satisfied because the intersection is by construction empty. So everything agree on the empty set. And then this matrix will be block diagonal. Thank you, Alex. This is a very good remark. Yeah. And it's obvious. It's just by definition. There's no need to argue here. Yeah. This is a very good point. 1, 2, 3, 4, 5. I still need 2 entries. So from 1 to 6, no. From 1 to 7, no. From 2 to 1, no. From 2 to 2, no. From 2 to 3, 2. From 2 to 4, nothing. From 5, nothing. From 2 to 6, nothing. And from 2 to 7, nothing. Now, from 3 to 1, nothing. From 3 to 2, nothing. From 3 to 4, 1. From 3 to 5, nothing. From 3 to 6, nothing. And from 3 to 7, nothing. Now 4 is a sink here. Nothing starts here. So here I just have zeros. 0, 0, 0, 0, 0, 0. Okay. Now, so 5. 5 is also a sink. 0, 0, 0, 0, 0, 0. But 6 is a source, but it has edges only to 2. And it has 1 edge. So it's 1 here, and everywhere else it's 0. And finally, 7 is a source, but it maps only into 4. So I have 1 in the 4th position. So 0, 0, 0, 0, 0. Jacek, can you do me a favor and raise this matrix to a 3rd power? And I'll do the other one. I mean, it has many zeros, but it's easier on a piece of paper. Yes, it's a 7 by 7 matrix with many zeros, and actually see that you have a lot of redundancy, right? Like these 2 rows are 0, and these 2 columns are 0. And I'll do the other part. So from, but why did I erase it? It's 1, 2, 3, 4, 5. We surely have 0 on the diagonal. Okay, so now from 8 to 9, I have 1. And that's it. And then I have from 8 to 12. So I have 0, 0, and then 1. Now from 9 to 8, 0. From 9 to 10, 0. Actually, 9 is a sink, so it's 0 everywhere. 10. Okay, it doesn't shoot anything to 8, doesn't shoot anything to 9, doesn't shoot anything to itself. When you go to 11, you have 1. But when you go to 12, you have 2. Now, 11. It doesn't shoot back, so you have 0, 0, 0. And it has 2 edges from 11 to 12, so 2. And then 12 is a sync, so you have 0, 0, 0, 0. Okay, so Jacek is computing the third power of this animal, and I will compute the third power of something simpler. So I'll write it next to it. So it's 0, 1, 0, 0, 1. Then the row of all zeros. Then 0, 0, 0, 1, 2. And 0, 0, 0, 0, 2. And another row of just zeros. Okay. So when I multiply it, I'll have, first one is 0. Well, actually, at the first column, everything will be 0 because this is a 0 column. When I look at the second, it will be 0. When I look, and again, the third one is a 0 because it's a 0 column. So 0, 0, 0, 0, 0. Now, fourth one, we have, this will miss this one because in the third place, and we have 0 in the third place. So it will be 0 again. And here I will miss everything. Yes, because in the second place I have 0, and the fifth place I have 0. So it again will be 0. Okay. Now the second row is a 0 row, so it will give me, wow, I have plenty of zeros. Now the third row, what will it give me? First one will be 0. Now with the fourth one, this is again 0. And with the fifth one, I have a first hit because I'm looking at the fourth and fifth place. So here I get 2. So I have 1 times 2 is 2. Wow, first non-zero entry. Well, and finally, now this one, so it will be multiplying the last row by zeros. Okay, so here I have zeros, 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 0, 0, 0. Okay, and now I have to multiply it again. So now let me multiply these two. And what will I get? I'll get first column is of course 0. Second, actually 4. Okay, all 4 of them are 0. So so this is one big 0. And I can only look what happens with the last column. And I'm looking at a row which has a non-zero entry at the third place. Now there's something wrong. I don't have such one, but it's impossible that I have a 0 matrix. But maybe this is the case. All right, yes, because look, there are no paths of length 3 here. Okay? So it should be 0. It is 0. The calculation doesn't lie. So Jacek, what is your matrix here? Okay. Uh-huh. 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 1, 2, 3, 4, 5, 6, 7. Okay. So that's it. Pair 0. So 4 plus 2 is 6. And let's count it by hand. So any path of length 3 starting from 1, well, we have 2. Okay. When I look at 5, 6, well, no, sorry. When I look at 2, that's it, 0. When I look at 3, 0, 4, 0, 5, 0. But 6, yes. I have, sorry, no, from 1 I have 4 because I have 2 times 2. So this will be 4 paths starting from 1, and I'll have 2 paths starting from 6. And this is exactly 4 by 2 that we have here. So you see, I did it on purpose because I can, for such a graph, I can find the number of all 3 paths in a flash. Whereas doing these matrices is much longer. But then when your graph is getting more connected, and all of a sudden you have like 128 paths, then matrix multiplication is more efficient. But I will need a volunteer to do it. I mean, I don't want that somebody shows how to multiply matrices. No, but I just want a matrix for the graph, its third power, and the addition of the entries for the remaining 10 cases. Okay? But the lecture is over, and let's resume at 2 o'clock sharp with recitation classes. Thanks.